Hello and welcome to this video for Chemistry 30 in the Equilibrium Acid-Base unit. In this video, we're going to look at the difference between monoprotic and polyprotic acids and bases. So first of all, for acids, if it has only one donatable hydrogen, it is monoprotic. So you're looking at how many donatable hydrogens does it have. Remember, when you have an organic acid, the only donatable hydrogens are the ones bonded to COO. Any H's as part of the ion is not donatable. So that is another monoprotic acid. When you have more than one donatable hydrogen, they're called polyprotic. Diprotic specifically if they can donate 2 protons, and triprotic if they can donate 3. So if we were to look at the following as being monoprotic or polyprotic, again, you're just counting essentially the number of hydrogens. There's 2 hydrogens here, so that is polyprotic. Oh, there's some sound effects in my video. I'm just going to turn it down. Here I have the COO ion, the COO twice. So both of those hydrogens are donatable. It is polyprotic. Next, there's only one COO, so only that hydrogen, and same with the next, only that hydrogen is donatable. So those are both monoprotic. Next, we have H2PO4 that can donate both of those hydrogens, so it's polyprotic. And for ammonium, it's just something that you have to memorize. It'll lose one hydrogen to make ammonia, and that's as far as it goes. So it is monoprotic. Now for bases, if it's a Bronsted-Lowry base, if it can only accept one proton, or if it's an ionic hydroxide and it has only one OH in it, then it's called a monoprotic base. So something that can accept one proton only is something like ammonia or an anion that has a -1 charge. Bases, on the other hand, that can accept more than one hydrogen are called polyprotic. So if it's an ionic hydroxide, it's polyprotic if it has 2 or more hydroxide ions in it, or as an anion if it has a negative charge greater than -1. So let's say we have PO4 3 negative. That is a triprotic base because it can accept up to 3 hydrogens, forming at first HPO4 2 minus, then H2PO4 minus 1 until it accepts the third to make H3PO4. So we're actually going to look with these polyprotic acids and bases at the process of them accepting multiple or losing multiple protons. Now the following are all amphiprotic species and is asking you to identify as acids and bases whether they're mono or poly. So the first one, as an acid, has 1 hydrogen, so it's a monoprotic acid, and as a base it has a -1 charge, so it's also a monoprotic base. The second one, as an acid, has 2 donatable hydrogens, so it's a polyprotic acid, but as a base it only has a -1 charge. So it's a polyprotic acid and a monoprotic base. Next, we have the hydrogen by itself, only 1 hydrogen, so it's monoprotic. And as a base, it has a 2 negative, so it's polyprotic. So it's a monoprotic acid and a polyprotic base. And the last 2, monoprotic for both of them. The reason water is monoprotic for both of them, again, is just something you also have to remember, that it will accept 1 hydrogen as a base to make the hydronium ion, or it'll lose 1 hydrogen as an acid to make the hydroxide ion. Okay? Now, if you are given the following words where you are told that you are either continuously adding an acid to a base or a base to an acid, or if the word titrated is used. If these key words are used, you are going to continue to react your acid or your base, transferring 1 proton at a time as an acid until it loses all of its hydrogens, or as a base until it gains the maximum it can based on its ion charge. So let's say you're told potassium hydroxide is continuously added to oxalic acid. So like before, we are going to list what we have present. we have potassium ions present, hydroxide ions present, and oxalic acid, which is HOOCCOOH. It is a polyprotic weak acid, so it stays a whole compound. And then we have water. So my strongest acid is the acetic acid, and the strongest base are the hydroxide ions. So what I'm going to do is react these in steps, as well as writing a net ionic equation. So in step 1, my HOOCCOOH, oops, there should be 2 O's there, OOH, is going to react with the hydroxide ion and 1 hydrogen. Now these questions are usually going to say that we're going to assume these are quantitative processes. So just a straightforward arrow. So I'm going to transfer 1 hydrogen. You're not done the reactions. I'm going to transfer 1 hydrogen, that was today's lesson, from the acid to the base. So when I do that, I'll form 1 HOH and HOOCCOO minus 1. It still has another donatable hydrogen. So it's going to react in a second step to make HOOCCOO negative 1 with a second OH. Again, there's a second OH because it says the potassium hydroxide is being continuously added. So we're going to transfer the second hydrogen ion from this organic acid to make a second water molecule, and OOCCOO2 minus. It now has no more hydrogens left to lose. Okay? So to write our net reaction, we cancel any intermediate species, something produced in one step and used up in the next step. You can always cancel things when they're on opposite sides. If they're on the same side, they add together. So we have 2 hydroxide ions in our net equation on the reactant side, and we are producing 2 HOH, and you can write that as H2O if you prefer, and OOCCOO2 minus. Notice how I'm not labeling the acid or the base, the conjugate acid or conjugate base. We commonly don't do that in these questions because there's just going to be a lot of writing. So you write the individual steps, the net, and that's it. Let's look at one more example, and then that's it for this video. So in the next example, we are titrating sodium hydrogen phosphate. So I dissociate that into sodium ions, and hydrogen phosphate is a polyatomic ion. I know it seems like there's 3 ions in this compound, but there's always 2 ions. The hydrogen phosphate is a polyatomic ion. It is being titrated with hydroiodic acid, which is a strong acid. So it is forming hydronium ions and the iodide ion continuously. Titrated means it's being continuously added. So our strongest base is going to be the HPO4 2 minus, and the strongest acid, again, if you don't remember how to figure out what's the strongest acid or strongest base, there's the video previous that you can take a look at that explains how to identify it based on the acid-base chart. So in step 1, now when I have a polyprotic base, again, it's polyprotic because of its charge. It will continue to gain hydrogens until all of the negative charge is gone. So this is going to, notice again how it says we assume the steps are quantitative, so fully forward processes. Now a base accepts a hydrogen from the acid. So this is going to make H2PO4 that still has a -1 charge, and H3O is going to be left as H2O liquid. Now in step 2, the H2PO4 -1 is still, like I said, considered a base because it still has a negative charge. So it can react with another hydronium ion, gaining another H plus to form H3PO4, and now all the negative charge is gone. So it's no longer a base, and that's where the reaction stops. Okay, so negative ions react if they're polyprotic until all of their negative is gone, if the question says you're continuously adding or titrating. So I cancel out my H2PO4. Again, that was called an intermediate. It was produced in one step and used up in another. And what I have left is my polyprotic base reacting with 2 hydronium ions. I'm producing the conjugate acid H3PO4 after it reacted with 2 hydroniums, and it's producing 2 waters. Okay, so that, I believe, is it for this lesson. Thank you very much for watching this video.